Hello, and welcome to this lesson on forces and elasticity. This is for the GCSE Combined Science course specialising in physics. Now, the major aim of this lesson is to try and understand Hooke's law. Now, in this lesson, our primary aims are to describe what Hooke's law is, understand what elastic and plastic objects are, and then state what the limit of proportionality is, which links into the following part of the GCSE Combined Science specification. Now, the major aspect we're going to look at in today's lesson is looking at the types of effects a force can have on a material, the equations to calculate the effect of the force on the material, and then ultimately look at how the energy stores in a material can change due to a force being placed on it. Now, in previous lessons, we've looked at the effect of resultant forces in the universe. Now, a resultant force can cause an acceleration for an object. A resultant force can cause energy to change between stores. Now, a change in energy stores due to a resultant force is called work done or mechanical work. But just be aware that work can also be done when electrical charge flows in a circuit. Now, there are three types of material deformation, which is the effect of a resultant force causing an object to change shape. Now, the first type of deformation is called extension. That's when an object increases in size due to a force being placed on it. Now, we're going to define extension as a positive change in length. Now, a force which causes an extension we call either a tensile force or tension. So when you apply a tension to a material, it will increase in size due to that tension. Now, for this to take place, more than one force has to be applied to the object because we're looking at resultant forces here. Now, the second type of deformation is called compression. Now, this is when an object decreases in size due to a force being placed on it. Now, in today's lesson, we're going to focus on extension, but just also be aware that all the mathematics and all the understanding of physics still works for compression as well as extension. Now, a force that causes a compression is what we call a compressive force. Now, we're going to define compression as a negative change in length. So when a compression is applied, the material gets smaller or shorter in length compared to before the force was applied. Now again, because we're looking at resultant forces, more than one force has to be applied to the object. Now, the third type of deformation is called bending. Now, that's when an object doesn't change in size overall, but it becomes distorted. So it stays the same size, but does change shape due to that resultant force being applied to it. Now, once again, please remember that for this to take place, more than one force has to be applied on the object. Now, we have just talked about there the ways in which a resultant force can cause material deformation. Now, there are two ways an object can behave if a resultant force is placed on it. And it can either behave elastically and be an elastic object, or behave inelastically and be an inelastic or plastic object. Now, an object is elastic if the object regains its original shape after the forces deforming it are removed. So here are all examples of elastic objects. When the deforming force is removed from these objects, the object returns to its original shape. Now, an object is inelastic if the object does not return to its original shape when the forces deforming it are removed. So in these examples, when the deforming force is removed, the object stays deformed. It doesn't return to its original shape. Now, sometimes the term plastic is used instead of inelastic. Now, the common term plastic, like plastic bottle or plastic bag, tends to be from the chemistry definition of plastic. Now, in physics, objects as well as the traditional plastic objects can behave plastically or inelastically as well as those polymers. Now, many objects in reality have an elastic and an inelastic or plastic region depending on the deforming force placed upon it. Now, at lower forces, the objects act elastically, but at higher forces, objects tend to act inelastically. So an object is elastic if the object regains its original shape after the deforming forces acting on it are removed. An object is inelastic if the object does not return to its original shape if the deforming forces acting on it are removed. Now, many objects are elastic at certain deforming forces and inelastic at the larger deforming forces. Now, the reason for the elastic and inelastic behavior comes from the atoms of the material themselves, because atoms in any material are bonded together. Now, in an elastic material, when the material is stretched, the bonds get stretched but don't break. So when the force is removed, the atoms go back to their original shape, because whilst the bonds have been stretched, they will go back to their same shape once that force is removed. But if a large enough deforming force is placed on the material, the bonds between the atoms start to fracture, so the molecules lose their original shape. Now, the atoms are fractured, like we said, when a large deforming force is placed on them. Now, this means the materials become inelastic. Now, eventually, if a very large deforming force is placed on the object, the bonds will eventually break, which causes the material to snap. So in this example, the bonds are being broken from the force being so large that the material itself will have snapped. Now, as we mentioned before, as this will cause material to snap because the molecules no longer can be contained next to each other and the shape loses rigidity. Now, Robert Hooke was the scientist who examined elastic materials by placing a deforming force on them. Now, he considered objects like elastic bands, but obviously it was a different object as Hooke was around 400 years ago. Now, he considered the following questions. What happened to the extension of an object when you increase the force placed on it, and what conclusion can you make from that? So he realized the following. The more deforming force placed on the material, the more the material extended. When some materials they had this deforming force, it would also work in direct proportion. So if the force was doubled, the extension was doubled. If the force was halved, the extension would halve. If the force was tripled, the extension would triple. And if there was a large enough deforming force, the material would snap. So here, for example, is a deforming force. Now, a deforming force will always cause an extension if it is a tensile force. Now, the extension is measured as the difference in length between the length with the deforming force and the length without the deforming force. So the extension can be considered as a change in length of material, or triangle, or delta L. Now, so it's the length with the deforming force minus the length with no deforming force. Now, again, like we mentioned before, the greater the deforming force, the greater the extension of the object. It would also be true for compression if the force wasn't acting as an extending or tensile force, but was rather acting as a compressive force. Now, in fact, Hooke realized that the extension and deforming force were in direct proportion to each other, which is now known as Hooke's law. Now, when Hooke plotted this relationship on a graph, he achieved a straight line trend in his graph. Now, this was again proof that force and extension are in direct proportion because we've got a line of best fit here with a straight line through the origin. And if you ever see a graph with a straight line through the origin, the two factors of the graph must be in direct proportion. Now, this is when the material is in its elastic phase. So, if the force extension graph of material is a straight line through the origin, the material obeys Hooke's law and it is acting elastically. Now, the graph has to go through the origin, as when the force is zero, the extension is zero. Now, if the line does not go through the origin, a common mistake students can make is that they've measured the length of the material and not the extension, which is a common question to ask in examinations. Now, Hooke realized that eventually, that if a large enough deforming force was placed on the material, it no longer had a directly proportional link with the extension. And the point at which this starts to occur is what we call the limit of proportionality. Now, after the limit of proportionality, the material acts like an inelastic. Now, eventually, if a large enough deforming force is placed on it, the material will snap, which we call the breaking point. So, therefore, Hooke worked out that all objects can either act as elastic or inelastic at different points of the force extension graph. So if it's a straight line through the origin, that's the elastic phase for a material, where it starts to curve that's your limit of proportionality, and then after it starts to curve, you've got your inelastic phase, which will eventually lead to your object breaking. Now remember, we said that if the line starts to curve, it's no longer directly proportional, so the material no longer obeys Hooke's law. Now, as well as looking at whether an object's elastic or inelastic, we can use the gradient of a force extension graph to work out a term of a material called the spring constant. Now, once again, remember, the graph places the force exerted on the object, the deformant force, as the y-axis. It places the extension of the object caused by the deformant force on the x-axis. Now remember, because this deformant force is causing an extension, the line should be going through the origin. Now if it does not, like we said before, it's probably because the experimenter has not measured the extension rather than measured length. Now the spring constant we can actually define as the amount of force needed to extend an object by 1 meter, which is basically how stiff an object is. The stiffer the object, the larger the spring constant, so the more difficult it is to extend. Now, the spring constant can only ever be measured from a straight line section of a graph or the elastic phase of the material. Now, that's because we're going to be working out the gradient, and the gradient has to be constant for the spring constant, as the name suggests. So it has to be the straight line section. Now, to take the gradient, you've got to draw a right angle triangle on the graph with a line of best fit providing a hypotenuse. Now you've got to make your gradient triangle as large as possible because it increases your validity results because you're considering more values. So you'll work out your change in y values, you'll work out your change in x values, and the gradient is then the change in y over the change in x, which is the change in force over the change in extension, or F over E, which we'll call the spring constant. Now it also allows you to work out the units of the spring constant because as we're doing change in y over change in x, the units are going to be the units of the y-axis, newtons, divided by the units of the x-axis, meters. So therefore, the units of the spring constant are newtons per meter. Now, the spring constant is the proportionality constant between the deformant force and the extension that it causes. So this means the equation for a material obeying Hooke's law is deformant force in newtons equals spring constant in newtons per meter times by extension in meters. But please remember, Hooke's law is only true for elastic objects. It doesn't work for plastic objects. Now, when this happens, the force, like we mentioned before, which is a resultant force, will also cause energies to change store. It will cause work to be done. So it allows your material to store energy as an elastic potential energy store. Now you can work out the amount of energy stored in the elastic material due to this extension via an equation you have covered in paper 1, which is that elastic potential energy store is a half times by spring constant times by the extension of the material squared. Now, the equation of Hooke's law, which is deformant force equals spring constant times by extension, does need to be memorized for your examination. It's one of those equations which AQA expect for you to memorize. Now, here's an example of a question which could be asked on Hooke's law. So a spring has a spring constant of 25 newtons per meter. How much force is needed to make the spring extend by 0.10 meters? So the force equals spring constant times by extension, so it's 25 times by 0.10, so it's 2.5 newtons. Notice I've checked that there is 2 significant figures in the question, so I'll give my answer to 2 significant figures, and I've also placed the correct unit of newtons on my answer. Now, just to clarify, right, for an object to obey Hooke's law, the line for your force extension graph must be straight. And the gradient of the line, when the line is straight, is the spring constant. And remember, the line has to go through the origin, otherwise extension is not being measured. Now, like we mentioned before, when the force extension graph shows a straight line through the origin, the material is acting as an elastic, it obeys Hooke's law. If it's starting to curve, it no longer obeys Hooke's law, it's acting as a plastic. It has exceeded its limit of proportionality. Now remember, when the object obeys Hooke's law, it becomes an elastic potential energy store. When an object does not obey Hooke's law, it is inelastic and is no longer storing its energy as an elastic potential energy store. Now, once again, like we mentioned before, when an object obeys Hooke's law, the force and extension are directly proportional to each other because it's a straight line through the origin. So, in today's lesson, hopefully we can describe what Hooke's law is, understand what we mean by elastic and inelastic or plastic objects, what they are, and finally we can state what the limit of proportionality is. Thank you very much for listening to this lesson on Hooke's law.